Okay, so good afternoon, everybody. I hope you have had great break for the last 3 days, I think, and then of course for your control there was a deadline regarding your project one, and I got one students that asked for an extension. So to let those that celebrate Raya, then we just give 2 days extension basically for your process control. Okay. We are nearing the end of our semester basically. Okay, so like I mentioned again, this is week 10. So I will have after week 10, then I will have 2 more lectures with you, week 11 and week 12. But the emphasis for you will be on your project 2. Okay, because your project 2 will be the one that are time consuming. So I think as previously mentioned, on from week 10, week 11, and week 12, I will only have one lecture. Okay, if I'm not wrong, there will be a Wesak Public Day, right? If not wrong, when is it going to be? Let me check again. There will be a. Wait, I have something outside, guys. I hope you will bear with me. I have post laju coming. just 5 minutes, guys. Sorry. Guys, sorry for the interruptions. Just post laju just call directly. So in this week, we're gonna discuss about the dynamic simulation of the distributed model. So we discussed already about in the previous lectures, we talk about the steady state simulation of the distributed model, where we basically discuss two methods to solve. One is the shooting method. The other one is the use of the finite difference method. Okay. So in an unsteady state distributed model, because we have a variable associated with the time, and we also have a variable associated with the coordinates, meaning we will have a set of partial differential equations. So in here, if we are dealing with the unsteady state distributed model, we will have to deal with these partial differential equations. And partial differential equations are the one that normally covered in depth in transfer phenomena. But my transfer phenomena is actually quite basic transfer phenomena, so we will not go into the details into how to solve these things. Okay, so if we talk about the PDE, partial differential equations, then there has been a classifications into the partial differential equation. So we have different. Oh, sorry, I'm not sharing my screen. Sorry. You see, I also forget about this thing. But thanks for you to share your to ask for this. If you don't ask me, then I. Now, is it? You guys can see everything that I share in here? Is it good now? Can see? Okay, good. Thank you so much. Sorry for that. Sometimes I overlook things. So in here I don't have anything to discuss, but the discussions is basically on the dynamic simulation of the distributed model. Okay. So like I mentioned to you earlier, if we have a variables of time and also the coordinates, which is the positions in our system, then we will get partial differential equations. There are different types of the partial differential equations, and it all has been classified and documented properly in advanced engineering mathematics. So if we want to go into solving all these different types of the partial differential equation, then there are established methods to solve that PDE. Basically, you can use a method of the combination of variables, method of the separation of the variables. You can also use a collocation, orthogonal collocation methods, and all the other methods that basically covers the partial differential equations. When we talk about the hardcore chemical engineering, the 20 years or 30 years ago, when the professors in the top university, they solve a transfer phenomena problem, then they normally dealt with partial differential equations and all these problems. Okay, as chemical engineering went on and advanced with time, then chemical engineering has many interfacing with the other disciplines, such as materials engineering and, for example, robotics, and then computer science. Then I think the emphasis goes away from those purely or dominated by the partial differential equations, basically. Okay, so a variable in two dimension can be considered as a surface. So if you have a variable that change with time, meaning that the surface will change as a functions of time, right? So in here we will limit ourselves to two types of unsteady state PDE, which is the parabolic PDE and the hyperbolic PDE. Okay. So the parabolic PDE is called a diffusion type PDE. Physically speaking, this means that we smooth out the initial conditions in space, and this PDE is exemplified by the conduction, viscosity, and dispersion in material, momentum, and energy balances. So these equations are the general form for the parabolic PDE or diffusion type PDE. So this is first order with respect to time, second order with respect to coordinates. And we simplify the presentation in that we only use one variable for the coordinate in Z direction. For the time, we only use T. Okay. So how do we solve these things, if you ask me? So we need to have the conditions. So the value of Y at a particular time. So normally it will be the value of the Y at time T equals 0. Okay. And then because this is second order, that means we need two different values of Y. Doesn't have to be just the value of Y. It can be a Dirichlet boundary conditions, meaning that you have the value of Y at any particular position of Z, or you can also have the derivative, the value of the derivative of Y at any with respect to Z at any particular position of Z. But because this is first order with respect to time, meaning you need one condition specified with respect to time and two conditions specified with respect to Z coordinate. Okay, so this has to be clear basically. Okay, if I go into the next one is the hyperbolic PDE or wave type PDE. So physically speaking, this means that in this particular condition, the initial condition will travel in space as waves. This is exemplified by convection in material, momentum, and energy balances. So different with the previous one is dealing with the conduction, viscosity, and dispersion, whereas this one is the convection in materials, momentum, and energy balances. The difference in here is that the derivative with respect to time is second order. Okay. So meaning you need another condition again that is specified with respect to time besides the initial condition, for example. Okay, so this is second order in both time and space. We have another one again after this hyperbolic PDE or wave type PDE that are classified as a special case of this hyperbolic PDE or wave type PDE. So that is called first order hyperbolic PDE or convection type PDE, which is described like this. Okay, so this one has a first order with respect to time and also space. So the method that we want to cover this times is the so-called method of lines. So this method of lines is the same with the finite difference method that we discussed in week, I think in the previous week. Okay, so this one is considered as a numerical solution for parabolic and hyperbolic PDE. What we do essentially is we discretize the PDE in space to give a set of ordinary differential equations in time. Then this ODE we solve using ODE solver. So the difference with the previous discussion is that in the previous discussion, we don't have a derivative with respect to time. So meaning that after we discretize everything, it all goes down to the solutions of matrix. Okay, but in this particular scenario, because we have the derivative with respect to time, and then we also have the derivative with respect to the position, that means after we discretize the derivative with time, we converted it into a difference, a finite difference form, then we still end up with the differential equation. These differential equations, you will have one for different positions, basically. Okay, this will be apparent as we go into the next slides. Okay, so the method of lines basically converting all this PDE into a large set of ordinary differential equations in time. This method is not the only method that you can use to solve or to discretize the space dimension. What you can use, other use is a finite volume and also the finite element. But we don't have time and to cover everything, so we will only cover the one of the widely used method, which is the finite difference method. So how do we do these things basically? So in the method of lines, we carry out the steps. So first you choose a mesh on the interval A to B. So in the A to B, you split it into different points, okay, where it has an internal grid points. So meaning your step size will be the right limit minus the left limit divided by the n internal grid points plus 1. And then if you use the same increment, then you can use this formula, xi plus 1 is equal xi plus h. Then you approximate the derivative by a difference method. After that, then you apply the derivative approximations on the PDE for each mesh point. As a result, you will have an n ODE for the internal mesh points. Then, depending on the boundary conditions that you have a von Neumann boundary conditions or you have a Dirichlet boundary conditions. If you have a Neumann boundary conditions, that means the derivative value is known, the derivative value of your dependent variable is known, then you need to also apply the finite difference into the boundary, meaning the endpoints, either in the left points, the left limit point or the right limit points, and also on the boundary conditions as well. So you have to use the method called the method of the fictitious point. Fictitious point in here meaning that the point is not really existing, but you imagine that those points are existing. They are present. Okay, that's why you call it, this one is a fictitious point. If it is a Dirichlet BC, then it's very easy because basically you can just put in the value of the dependent variables at the left or the right limit. Okay, so at the end you will have the ordinary differential equation system of n plus nb ODEs. If you're dealing with the Neumann BCs, if not, then you will only have an n ordinary differential equations. After that, then you proceed with solving the ODE. Like what we mentioned earlier, generally those ODE will be stiff. Stiff meaning because you have a different behavior with respect to the different parameter, right? Like if in the case that I showed you in the previous lecture, there was a variables of the temperature, if not wrong, and then there was a variable of the concentrations, I think, right? So they may behave, they may have a different time characteristics, for example. So in this regard, it is recommended that you use an ODE 15S. Okay, so how do we do the space discretization? It's the same that we do on the week 9. Okay, so if we have this del X over del Z, then we need to use this approximations in here. Note that in here, the convection term cannot be treated in the same way as the first order derivative. Okay, we have to approximate it, the first order derivative, using a backward Euler approximation. The division term in here can be approximated by the same method as in the steady state problem. So if we use the center difference approximation, it will look like this. Division term can be first order if the discretization is done on cylindrical or spherical coordinates. If for this term that we have in the spherical coordinates, for example, it can be approximated by this term here. I want to highlight a little bit on the second order and the first order approximation, okay? If you use a first order approximation, then the error will be higher with respect to if you use a second order approximation. So second order approximations will be a much better approximation with respect to the first order approximation. So in order for us to understand those things that we have discussed, but except this time we apply into partial differential equations, then we will discuss an example in here. The example in here is on the steam heated plug flow heat exchanger. So imagine that without deriving this partial differential equation, we just try to solve the PD in here, where we have del T over del T is equal minus V del T over del Z plus 4U divided by rho CPD multiplied by Ts minus T. And we have one initial condition in here. Oh no, this one is actually the boundary condition because this one is at Z equals 0. Okay, and then this one is the initial conditions. So T is equal Tz at T equals 0 as the initial condition. Meaning that because we said that this is a steam heated, meaning that the steam is heating this plug flow container basically. Okay, so the first step that we need to do is we select a grid. So let's say imagine that we are taking as the left limit is 0 and the right limit is L. So the mesh size will become H is equal L minus 0 divided by N plus 1. The second step is we apply the discretization method. In here, we discretize the convection term using a backward difference. Okay, so we replace this particular terms with this particular approximation. So if we substitute this into this, okay, what we'll essentially get will be this particular form we apply. And then we are dealing with the simple boundary conditions in here that everything is equal T is equal T naught at Z equals 0. Okay, so that's what we need to do. And then let's assume that we have the following parameters specified. The velocity equal to 10, heat transfer equal to 2500, density equal 1000, heat capacity equal to this, tube diameter is equal 0.1, length is equal 0.5, steam temperature 120, and the inlet temperature is equal to 25. So these are our wet lab. If I go into the details, essentially what you have is these things in here, right? Imagine we have a 10 internal points. So you will have 10 equations basically. The first equation is simply you substitute the value of I into this particular equations. If you do these things for I equal 1, you will recover this particular form. If you do it for I equal 2, you will recover this particular form. If you do it for the third grid points, you will have this internal grid points, you will have this. Okay, and so on basically. So actually you have 11 because you have n plus 1 grid points, right? So if we continue with these derivations, we will know that, let me put it into a rotate view so that it's going to be more clear for you, right? For n equal 3, what you have is essentially this one. For the first grid point, the second grid point, the third grid point, the fourth grid point. So each ordinary differential equations for each individual grid point in here. Okay, so you start from here, you will get this one. So what you need to solve is this particular matrix. Okay, then you notice that this particular form of the matrix has a special form in here that you can make approximate using this particular command in the MATLAB code to make it easier to code, right? So that's what we did in here. We basically do these things in here, and then your ordinary differential equation, your set of ordinary differential equation is basically represented by this particular line of the code in here. Okay, so how do we solve these things? How do we solve these things is we just use ODE15S. We call that particular function that define the ordinary differential equations. We give the initial value, which is this one, and then also the range of the time where we want to solve. For example, this one from 0 up to 0.1. Okay, then we put in comments to plot. Okay, in the different representation, we put in figure 1 and figure 2. So this will be what happens if I put in 10 internal grid points. Okay, each of these points specify the temperature at different grid position in here. Okay, and this one is at different time. So for example, in the beginning, everything will be the same. But as you go to 0.03, then the temperature will be different at different grid points. Okay, and after it's reaching steady state, then at 0.1, then you know that basically these are the different temperature at the different grid points. Then you want to check, for example, if you increase the number of the internal grid points up to 100, then what will happen? So you will have something that are more having a high resolution in here. Okay. Then we can also pick another representation. For example, instead of plotting it with time, we can plot it with respect to the tube length. So this one is what happened with respect to at time t equals 0. So the temperature is similar, right? At time t equals 0.02491, it will be this profile, right? And then the next one, and then at 0.1, you will have something that varies like this, basically. Okay, and the positions in here denote the time at different tube length. Okay, so that will be my example for today's dynamic simulation of the distributed model. Is there any questions from anybody? Is it clear enough, my explanation for today? Anybody? Any questions? Clarence, Daniel, James, Jason, Jonathan, Juliana, Chising, Michael, Taha? Rachel, Tiffany, Yusing, Wang Yo, Wei Xing. Anything that you want to ask from the discussions on this week, or anything that probably you want to ask about the other things? Okay. No, all good. So process modeling and optimization. Process modeling is actually a very broad subject. It's something that consisted of two different aspects. The first one is the formulation of your physical chemical problem. You convert it into a mathematical model. That thing entirely is something that are not easy in itself, because depending on how you want to put in on what assumptions, then that will be a big area or a big things to tackle. The other thing that we cover in the process modeling is also, once you get the mathematical model, how did you solve it using a numerical solution? So that's why within this past 10 weeks, we have been covering so much different materials because of the very broad materials that we have to cover with respect to the process modeling. Okay, even somebody that has been doing, for somebody that has been doing research in chemical engineering for many years, then doing the formulations or doing the solution itself is not really something that are quite easy to do. We will go a little bit deeper into this when we go into the transfer phenomena. Transfer phenomena has a higher level with respect to the process heat transfer, because in transfer phenomena, you basically have the formulation issue. Okay, so in process heat transfer, of course, you have a formulation issue, but in most of the times you are given a dedicated formula to deal with the specific scenarios. Okay, process heat transfer, the difficulties probably in trying to understand the applications and the specific cases. So how you plug in the different scenarios. But in transfer phenomena, the level is a bit different because the formulation can be on a different geometry, on a totally different scenarios, and then something like that basically. So that will be a bit different. So before I go before I conclude these things, I would like to give you some tips into next week take-home assignment. Basically, I want you to go back into the materials that are covered. For example, the Euler method in here, right? The Euler method in here. So, for example, the numerical calculations in here. How do we solve these things? For example, if we are given a specific problem, how actually did you do the calculations for Range-Kutta method, for example? Range-Kutta method. I want you to have an understanding into how you can implement these calculations manually. Okay, so that's one is very important, so that you also know how your code is working. Okay, it can be a Euler method as well. For example, you can try to repeat these calculations in order for you to be able to familiar yourself. Okay, and then if I go, for example, with the half interval method in here, if you go into the examples in here, how did you solve a half interval method, for example? How did you iterate using this half interval method? Or it can be a regular falsi method, for example, or it can be a direct substitution, for example, because we give you an example of how we calculate this direct substitution. And then the Newton method, for example, how do you do in iterations? How do you pick the initial guess of this? So some part of this may come out in your take-home assignment too. So you need to pay attention on these things. Okay, that will be a good tip for you. Another thing that I want to talk to you is please, on your peer assessment for the project 2, please don't just go and do it quickly. Please read carefully the guidelines. Okay, spend time properly on your peer evaluation. And treat these things very importantly, because this will have an implications to your final score. Okay, so for example, You need to be serious on these things. If the total assigned score has, under each criteria, please ensure the total score you assign to all members is kept at 7 times number of members. So for a group of 3 members, the total allowed score is 7 times 3 equal 21. For example, if I make a group with Hannah and I make a group with Frederick. Okay, so if I think myself is the one that are performing much more than the other people, I contribute much more, then I would like to give a score of 8. Okay, 8 or let's say 8. So meaning 21 minus 8. 21 minus 8 meaning how much I have remaining. 21 or 21 minus 8. Okay, let me go again into this calculator, because I don't want you to do these things just for trivial. So I have the remaining of 13. Okay, 13 meaning I can 7 and 6. So let's say if I think that Hannah is performing the best after me, I give her 7. Then I only have another 0.6 points to give to Frederick. If I think that all my members are performing equally, so for example, Hannah is very responsible, Frederick is also very responsible, then I give them 7, 7, 7. So if you give in, for example, I give in 10, 10, 10, so that will be 30, basically. So that means you need to read the next line. If the total assigned score has exceeded the limit, the balance will be deducted from your score. So meaning 30, if I put in 10, 10, 10, meaning there will be 9 extra point. So that 9 extra point will be deducted from 10 that I give to myself. So meaning I only give 1 point to myself. The other 10 points are given to the other 2 members. Okay. Then please rank your teammates as well. So cannot have multiple members getting the same ranking. Kindly list down your comments in the final section. Student will get 0 mark if this assessment is not submitted. I mean, you will get 0 mark in the peer assessment. Not 0 mark on your project 1, no, but 0 mark in your peer assessment. So this is very important, because if you and your group mates are performing equally well, everybody cooperate with each other well, then most likely everybody will get 1 normalized factors. Okay, so this is quite important, because we know that as we form a group, sometimes we have limitations that I cannot just interfere directly into the group arrangement as well. Okay, or I choose not to interfere directly into the group arrangement, basically. But this will basically give a sense of the fairness into how you contribute into your project. Okay, so those are the things that I want to cover for today. Do you have any questions? Anybody have any questions? Anybody? All good with your process control, with your process modeling so far? So for process modeling, remember that we will have a take-home assignment next week. Okay, we have announced that thing in the canvas, so just pay attention on the time, and then I already give you a tip on the take-home assessment too as well. If you still need any help with regard to the process modeling and process control, then you are free to contact me as well. If not, then I think I will let you do something else again. Probably you can go with your project 2 or any other assessments or assignment that you want to prepare with. Okay, everybody. Then that will be all for today. Let me stop the recording.